Hello there, my name is Aus Naman, or in my native tongue, Aus Thabit Nu'man, and you are very welcome to join my session where I will talk about encoding high-throughput JPEG 2000 images on a GPU. For those in a hurry, I have a summary at the start. Since high-throughput JPEG 2000 HTJ2K is new, we try to give a short description here. It's a new addition to the JPEG 2000 suite of image coding tools. It's known as Part 15 and it uses the .jph file extension. So what do we gain from high-throughput JPEG 2000? We gain a much faster block coder, at least 6 times, but can be as high as 30 times faster than the conventional block coder. It is more efficient than JPEG, faster on a single core, and can scale almost linearly with the number of cores. What do we lose? We have lower coding efficiency and an increase in PD rate of 7% or a loss in PSNR of 0.7 dB. We have reduced quality scalability, although resolution scalability can be used as a proxy for quality. Accessibility and resolution scalability are still available. An advantage of high-throughput JPEG 2000 is the lossless transcoding to and from JPEG 2000. As you can see, implementations already exist. In a previous work, we have shown that hundreds of frames per second can be decoded on a mid-range GPU. This work explores encoding on the GPU, and we show that hundreds of frames can be encoded on the same GPU, but lower than decoding. This is where those in a hurry can leave. The JPEG 2000 pipeline includes a color transform that puts the image in a form more suitable for compression from the human visual system's point of view. At the bottom, we can see the original image on the left and its color transformed version in the center. Then we have a wavelet transform. The wavelet transform exploits spatial redundancy. On the bottom right, we can see the image after one level of wavelet decomposition. We can see that the wavelet decomposition produces a sparse representation that is easier to code, since most of the coefficients are close to 0. Subband wavelet coefficients are then partitioned into rectangular areas known as code blocks. Examples include 64 by 64 code blocks and 32 by 32 code blocks. The rest of the talk is about entropy coding of code blocks. JPEG 2000 parts 1 and 2 employ a fractional bitplane entropy coder. Each bitplane is coded in 3 coding passes known as significance propagation pass, magnitude refinement pass, and cleanup pass. For example, 3 bitplanes have 7 coding passes. This is because the first bitplane can only have the cleanup pass. The cleanup pass in high-throughput JPEG 2000 is different in that multiple bitplanes are coded at once, as shown in the figure. A high-throughput JPEG 2000 entropy coder can also produce SPP and MRP. This enables transcoding to and from conventional JPEG 2000 and provides finer granularity for bitstream truncation. In this work, the encoder produces one cleanup pass only. In this case, the encoder directly encodes the data produced by the quantizer. This is similar to how most JPEG encoders operate. The bitstream encoded this way should be very close to optimality in rate distortion sense, especially at mid and high bit rates. We do not employ any rate control. However, high-throughput JPEG 2000 supports single-pass precise rate control. The high-throughput JPEG 2000 cleanup pass is made up of a magnitude sign segment, a mel segment, and a VLC segment. At the end of the cleanup pass, there is a pointer to the start of the mel segment. The pointer is the total length of the mel and VLC segments. In this work, the encoder doesn't produce significance propagation nor magnitude refinement passes. Notice that the magnitude sign, mel, and SPP grows forward, while VLC and MRP segments grow backwards. The advantage of having these multiple identifiable segments in the code stream is that this provides the encoder and the decoder with opportunity to concurrently operate on these segments. Coding efficiency is obtained by efficiently coding the locations of non-zero or significant coefficients. and information about their magnitude. This is true for all JPEG, JPEG2000, among other schemes. The high-throughput JPEG2000 cleanup pass encodes samples in 2x2 groups, known as quads. See the figure. The VLC segment interleaves two types of information: context-adaptive variable-to-variable codes in context VLC and new values in new VLC. The context is obtained from nearby samples that has been coded before, as shown in the next figure. The context VLC code for a quad communicates the location of non-zero samples in that quad. It also communicates an indicator of the existence of U values in UVLC for that quad, and A and B values that are explained in the next slide. The magnitude sign segment communicates coefficient values by packing them, that is, no entropy coding is done. One way to describe a quantized coefficient is as an unsigned value mu and a sign s. The encoder encodes 2mu plus the sign, which occupies the least significant bit. We define an exponent capital E as the smallest number of bits needed to encode 2mu minus 1 plus sign. We also define Emax for the maximum exponent in a quad. Thus, Emax is the number of bits needed to represent sample values in the quad. We do not communicate Emax, but we indirectly communicate an upper bound capital U, which is larger or equal to Emax. The idea here is to predict capital U and increment it if it is not large enough. This involves generating a predictor kappa from exponents in the previous row, as shown in the figure. If kappa is larger or equal to Emax, then we set capital U to kappa, signal the absence of small u from the byte stream by setting U offset to 0. Alternatively, if kappa is smaller than Emax, then capital U is set to Emax. U offset is set to 1, and we communicate small u, which is the difference between Emax and kappa. Capital U is the number of bits that needs to be communicated for each sample in the quad. If capital U is larger than Emax, all the MSBs in a quad are 0, which is not ideal because we do not want to send zeros. But this arrangement has better coding efficiency than employing a signed small u and paying the cost of the signed bit. The A and B code decoded from the context VLC is used to communicate some MSB values. The A and B code reduces the number of bits that needs to be communicated in the magnitude sign segment, but increases by a smaller amount the number of bits in the context VLC. The MEL coder is an adaptive run-length coder that efficiently encodes runs of 0 events. A 0 event occurs when a quad whose context is 0 has all of its samples quantized to 0. That is, its context is 0 and all its samples are 0. The figure shows the context for a quad. The MEL coder is useful to encode runs of all 0 quads, which usually occur when a subband is coarsely quantized, and therefore most of its samples are 0. Now we have a recap. Notice that for the VLC and magnitude segments, producing data for a quad depends on the adjacent quads only. This provides more opportunities for parallelism. Also, coding efficiency is obtained by efficiently coding the locations of significant coefficients using context VLC and information about their magnitude in the form of capital U. High-throughput JPEG2000 is very suitable for GPU implementation. The Wavelet Transform is highly parallelizable. Additionally, there are thousands of code blocks per image that all can be processed in parallel. There are also 3 segments per code block, where we can process one segment in one CUDA kernel. Segments except MEL are highly parallelizable. We have one CUDA thread per 1 or 2 columns of samples or quads. MEL is only needed on a small number of quads. We envisage 2 scenarios. In one scenario, the CPU uploads uncompressed images, which are compressed by the GPU. This requires high upload bandwidth on the PCIe interface, which limits the number of frames processed in a second. In another scenario, the CPU uploads high-throughput JPEG2000 images that are decompressed, processed, and compressed back on the GPU. This requires less bandwidth on the PCIe interface, but more compute resources. The CPU is responsible for downloading the compressed code blocks and packaging them into files. A special kernel is used for the first level of wavelet decomposition. It performs color and wavelet transform. This saves bandwidth by eliminating the need to write intermediate results to memory. We refer to this kernel as KCT plus DWT. The following wavelet transform kernels perform the wavelet transform only. The kernel produces 32-bit floats for further decomposition and 32-bit integers for entropy coding. Each CUDA thread operates on 2 columns. However, a warp comprising 32 threads can only produce a number smaller than 64 columns of coefficients because of the overlapping nature of the wavelet transform. The first entropy kernel is the magnitude sign kernel, denoted by Kmag sign. It reads quantized coefficients and produces the magnitude sign segment. It also produces some state information used by subsequent kernels. Compared to other implementations, we save bandwidth by reading uncompressed data in this kernel only. Here are the other entropy coding kernels. We have the VLC kernel that reads state information and produces the VLC segment. It also packs mel events. We also have the mel kernel that reads mel events and produces the mel segment. The last kernel is a copy kernel that copies the VLC segment to the end of the mel segment, potentially overlapping the 2 segments. It also produces the pointer at the end of the VLC segment. The GPUs used for producing the results are a low-end GT1030, a mid-range GTX 1660 Ti, and the 2-generation-old high-end GTX 1080. Experimental results are shown in the next page. We notice that the color and wavelet transforms take around 50% of the overall time. We also notice that entropy encoding is dominated by the magnitude sign. This is because of the high memory bandwidth required by this kernel. We also notice that we can encode hundreds of frames per second, while for conventional JPEG2000 the number is in the tens. Next, we have some kernel timeline plots, which I will skim through. On the timeline, kernels are marked for 1 frame. At the top, we can see the time. The same is true for this timeline. The high-throughput JPEG2000 standard is an exciting new addition to JPEG2000. It has significantly lower complexity. It enables parallelizable implementations that are an order of magnitude faster than JPEG2000 parts 1 and 2. Block coding has similar complexity to color wavelet transforms. Therefore, rate control can be very fast, since an existing CPU implementation shows that 2 carefully chosen cleanup passes are sufficient. High-throughput JPEG2000 is transcodable to and from conventional JPEG2000 parts 1 and 2. Very fast GPU implementation is possible, encoding hundreds of frames per second. For future work, we intend to implement the significance propagation and magnitude refinement passes. We also intend to implement a rate control mechanism. Finally, we intend to publish complete results for high-throughput JPEG2000 encoder-decoder implementation on a GPU. Thank you.